With the rate of improvement of processing power slowing, there is a need for greater design sympathy in order to achieve performance gain. As such, today on Lokad TV, we're going to be discussing the law of small numbers and how it can be exploited to improve supply chain performance. So Johannes, as a company that kind of specialises in big data, it's probably surprising we're talking about small numbers today. So what's the idea?
So the idea is that small numbers, not large numbers, are ubiquitous in supply chain. And when I say small numbers, I'm specifically referring to all the numerical choices, numerical quantities, that really matter. I mean, yes, you can have a barcode, that has like 13 or 14 digits, but they are a bit inconsequential. You treat your barcode as an identifier, not as a quantity. So when you look at things that are like quantities, what is very surprising is that it's always about very small numbers all the time. And when I say very small numbers, I mean, single digit small, like super small. And it's very intriguing because most statistics are geared toward the laws of large numbers. And then I would say in terms of computing, you would think, well, it doesn't matter for a computer, a number is a number, right? It doesn't matter. It turned out it does. It does quite a lot. And you'd say, well, I was under the impression that, for a computer, they can do an addition like that. Yes, they can. They can do computers can be super fast in doing an addition on two numbers. But the question is, what kind of numbers? And if you correctly choose your numbers, and we can get more into that. Well, it turned out that your computer can not only be fast at doing those additions or just mundane operation with number, they can be like something like 20 times faster, 10 times faster. So it makes a big difference in the end. It's not like a small difference.
Okay, so maybe for people who perhaps are not so aware of what happens when computers send information, what do you kind of mean by sending a number? How can that be different between one system to another?
So that's here we are going into the details of the physical reality of the computing hardware that we have. So why does it matter? Well, because if you want to do supply chain optimization, quantitative supply chain optimization, you're going to do a lot of data processing, data crunching, and that costs money. And actually, even if computers nowadays have become vastly cheaper than what they used to, the thing is, if you have something that is vastly cheaper in terms of raw processing power, then you can do you can have better, more, I would say, extensive, more powerful algorithms to do basically to give you the next stage of forecasting accuracy or performance in terms of supply chain optimization. So you see, there is always a balance between the computing cost and the supply chain performance, numerical performance that you can achieve. If your raw computing cost is lowered vastly, then in turns, you could say, oh, then the computer costs are going to vanish to nothing. But it's not true, because you're going to leverage your newfound resources to basically have a more complex model that can do better, and thus that will just increase in turn the computing cost. Thus, you need to pay a bit of attention to that. Now back to those numbers and law of small numbers. In computers, especially enterprise systems, most of the need toward calculation, arithmetic calculation, originated from I would say the world of finance. The first enterprise systems were all geared toward accounting, finance, supply chain. That's what emerged in the 70s. Supply chain came a bit later in the 80s, and a lot of the practices that were already established at the time, especially with regard of the high precision numbers, were imported into supply chain. So why do you need super high numerical precision for money? Well, it turned out that in the early 80s, there were a lot of relatively spectacular frauds where people had just used the fact that when you round the cents, you can actually create magic. You can actually steal money if you just round a few cents in every single transaction that your company is making. And it's completely invisible for the system because it was rounded away, but actually it was real money. And people, when you had like billions of transactions, some people were managing to literally extract millions of dollars out of the system by just taking only the fraction of a cent and redirecting them to their own accounts. So the world of finance and accounting upgraded to very high precision numbers where those problems don't appear. The problem is that I would say, supply chain did too, but as a result, you have numbers that are like super, super high precision by default in pretty much all the systems. And you have to ask yourself, what is the usual quantities that is going to be bought by a client in a store? And our answer at Lokad, because we observe the data, is 80% of the transaction in a store is the quantity is just 1 for the product. So literally the question is, you have a number, how many bits of precision do you need? Well, the answer is you need something like 2 bits of precision on average to represent, a number in a store, for example, for a quantity being purchased.
But why should we really care about how many kind of bits are used to send data? Because, I mean, if we're looking at the whole entire supply chain, I mean, does it really make that much difference in the whole grand scheme of things?
You would think that nowadays you can buy, hard drives that are terabytes at literally your nearby supermarkets for just something like 1 terabyte is probably something like $200 or something. So you would think it's super cheap. Why do I even care about that? Well, it turned out that the performance of most calculation is literally driven by the size of the data. If the data is bigger, it's going to be slower. Why? Because the bottleneck is not your CPU, it's just loading and unloading the data. Yes, you can buy a hard drive that is 1 terabyte, but if you actually try to just fill this hard drive with data, it's likely to take 1 or even 2 days just because the drive is slow. And so just literally writing data on the disk or reading the disk entirely takes a very long time. So it's not, again, if you can just minify the data, you can literally accelerate significantly the computation. And when I say significantly, usually you even have like super linear gains. So if you divide the size of the data by 2, you don't speed up the calculation by 2, you speed up the calculation by more than 2. And we have seen at Lokad that there are many situations where when we had managed to shrink the data by a factor 10, we were literally having like a 50 times speed up. And again, if we go back to our numbers, let's go back. We had a double precision number, so 64. By the way, what it's called a bit in computer science is just a 0 or 1. And so if you have a number that is represented with 64 bits, compared to a number that is only represented with 2 bits, well, you have literally 32 times more. It takes one number literally takes 32 times more space. So if you can compact vastly those numbers and turn this big data into much smaller data, you can have computation that is much faster. And
but
that's, yeah.
Supply chains are still kind of dealing with all of that kind of big financial data as well in terms of some of the transactions they have to do. So how are you kind of sorting between what needs to be kind of smaller data and what should be kind of the bigger data?
So literally you don't want your supply chain specialist to pay attention to that. You really want to have a platform like Lokad, shameless plug, that does that for you. But my message, my broader message is that somebody has to pay attention. It can be your vendor if they are very careful with their technological stack. It can be your IT department if they are very careful in the tools that they choose. But in the end, somebody has to pay attention. If nobody pays attention, what you end up with is systems where you have like massive amount of computing hardware, and for performance that are usually completely disappointing, where it literally takes seconds to get a result, and even seemingly semi-trivial calculations takes quite a long time. And the idea of having the way we see the supply chain of look at all possible futures with probabilities, confront that with all possible decisions, this idea just remains a distant dream, just because the system is already so slow just to cope with one scenario, so one possible future, that the idea of having the system dealing with millions of possible futures is a complete lunacy.
But yeah, if we're looking at all possible futures, all possible decisions, surely that goes against the whole kind of goal, which is to kind of reduce compute cost. But if you're looking at all possible futures, surely that's going to multiply that compute cost by far more.
Yes, but that's the trade-off that I was describing. If you make your computation much faster, you don't want to just have like a super cheap computer to run your entire supply chain. If we were still using the techniques used in the 80s in terms of supply chain optimization, we could on a smartphone we could literally run Walmart with a smartphone. A smartphone of present day can, if you stick to super basic, moving averages, you can literally, run Walmart on a smartphone. Doesn't make any sense to do so, but if you're just up to the challenge of proving the point at how incredibly scalable moving average can be, yes, you can run Walmart through moving averages on a smartphone. Now, if you want to have something that is better, where you have like the cyclicities, day of the week, day of the month, seasonality, patterns, trends, cannibalization, whatnot, suddenly it's not possible. So the idea is that when the computation becomes cheaper, what do? You adopt a mathematical model, statistical model, or an optimization model that is just more powerful, that deliver better supply chain results at the expense of consuming more computing resources. So it's a trade-off. But the interesting thing is that even if we say we look at all possible futures, this whole idea of laws of small numbers, it still apply. When we say all possible futures, do you need to, let's say, for example, in a store, to look at all possible futures, you need to look at the probability if you were to sell 1 million bottles of Cokes in a single store in a single day? Well, the probability is just zero. You're not going to sell 1 million bottles of anything in your, even in a large hypermarket. It just cannot happen. It will not happen. So the reality is that maybe, even if you take like a flagship product, it's very rare that you're going to sell more than 100 units any given day for any given product. And for the vast majority of products, even if you're looking at a fairly large hypermarkets, you're only looking at 0 units of products that are going to be sold. That's actually the majority of products, like 80% of the product of the hypermarket are not even sold once every day. And maybe for 95% of the products, the question will be only, do I sell this product like 0, 1, 2, or 3 units every given day? And the probability that you can even reach 10 units is already vanishingly small. So again, law of small numbers.
Okay, but in that kind of hypermarket example, they're dealing with sort of thousands of transactions a day, and you've got massive kind of stock holdings. So how do you know where to draw kind of the limits for each of the individual items?
I mean, that's where you basically need, again, the proper tooling that analyze data, the historical data. So you're guided, you're guided in your analysis. Because when you look at the historical data, but also, a good supply chain software, especially, of the predictive kind like Lokad, there are things that up front, you're not discovering that, an hypermarket for the first time. You know that it's the way it works. And yes, you have many transactions and many products being sold, but you have so many different products. So when you look at every single product, you don't have that many transactions. I mean, if you look at the fact that a product is going to, have a life cycle on the market of maybe 3 years, then it will be replaced by another product. If you look and that the product is not even sold every single day, it means that maybe to reach a point where you have like 100 units being sold in your entire sales history for this product, which would be maybe the lowest level 100 units to consider that you have a large number. I mean, saying that 100 is a large number is quite a stretch, especially from a statistical perspective. But that would be like a low bar for that. It might actually take more than a year. So that means that if you have a statistical tooling that is designed around this idea that you will be able to leverage, laws of large numbers, it will maybe take more than a year so that your tool even start to become relevant. And remember, we are talking of a product that is only going to have like a 3 years life cycle. So it means that for a third of its lifetime, the many statistical tools will not even be relevant.
Okay, a lot of companies kind of consolidate their sales by kind of week or month. How well does that work if you're kind of getting probably a perceived kind of performance gain? How much does that work compared to the trade-off of you're kind of losing a bit of granularity in your data?
So that's very interesting because I said, you have those problems of the laws of small numbers are ubiquitous. And the problem is that all the tools, at least the classical tools, certainly not Lokad, but the classical tools certainly are geared toward the laws of large numbers. So what do? Well, you aggregate stuff. And why do you aggregate? Not because it's the right thing, but just because it's a way so that you can end up with results that are not completely dysfunctional. But you're not doing that because it's something smart and relevant for your supply chain. You're just doing it because otherwise your logic that is driven by averages would just fall apart, because again, implicitly what you try to leverage is the law of large numbers. So indeed you consolidate, but the point is that when you, for example, consolidate decisions up to monthly aggregation so that you can have bigger numbers, the problem is that your supply chain decisions are still taken on a daily basis. So yes, you have a better monthly analysis just because you've consolidated all the data, but you're still taking decisions on a daily basis. And it turned out that your monthly analysis doesn't tell you anything about what is happening within the month. So yes, you know that over a month, you have 100 units that are being consumed on average. Now, today, should I push 0, 1, or 3 or units to the store? And then and similar decisions also exist when you aggregate not time-wise but category-wise. So if you, for example, say, okay, today in terms of sodas, I sold 500 units. Yes, but it was spread over 100 product references. So it doesn't really help, because in the end, in supply chain, you're not taking a decision at the category level, like for example, the fresh food segment. You don't take a decision at the level of the fresh food segment of your hypermarket. You take a decision on this specific product reference and what should happen with it.
Okay, we start sort of wrapping things up then. For somebody kind of watching this, what should they be looking to exploit in order to introduce kind of that design sympathy and make the best use of the processing power that's kind of at their fingertips?
They should really start looking, revisit. First, I would say on the statistical side, I really suggest to revisit all the core assumptions. I mean, whenever people tell you, oh, we have safety stocks, yes, it's normal distributions. Again, you should really ask yourself, am I looking at a problem with the statistical tools that are relevant for literally the laws of small numbers that I'm facing? And if basically, and most of I would say the 19th century statistics that people are using nowadays are clearly extensively geared toward laws of large numbers. So my suggestion is beware. The tools that you are using are not designed for the kind of situation that you're facing. So, and again, we are going back, to pseudoscience and fake rationalism. It's not because you're using a mathematical tool that it makes it rational. Maybe, your tool, your statistical framework that you're using came with core assumptions that are just violated by your domain. So I would say, revisit the basics, make sure that you're not missing something big. And then in terms of mechanical sympathy, I would say my message is, it's just like the great champions, for Formula One. When it's very funny when you see interviews of the champions, they know a lot about their cars. They don't know how to build a Formula One, but they know the mechanics. They have what is called the mechanical sympathy. They know a lot about how the car works, so that they can really get the best of the machine that they have. And they literally know a lot about combustion, about resonance, about the right temperature for the tires, so that you have like maximal adherence to the ground. I mean, they know a lot about the technicalities and the physics of their engine. And that's how they can become really great pilot. It's not just being good at driving. It's knowing the tool that you're using. And I believe supply chain is a bit like that. You know, you're not driving a supply chain by sheer muscle. Nowadays, you have computers to support you. But if you really want to be very good, you don't have to become, you know, an engineer that is capable of producing a Formula One. That's not, you know, a pilot is not, you know, is not like the mechanical engineer that is able to design the next generation of the engine, but they know a lot to get the most out of it. So my suggestion is get enough mechanical sympathy about all those computer systems that support your supply chain so that you know intuitively what makes those things tick and how you can, you know, really max out the performance that you have.
What we're kind of seeing at the minute as well with kind of industry is more data, and people are collecting more data to make all their kind of decisions. So would you say that kind of perspective is really moving away from that kind of law of small numbers and people are more heading towards kind of a big data perspective?
Again, the problem with that is that the data that are the most important are always in small numbers, you know. Yes, you can collect massive amount of data on your website for the traffic. But if you look at the traffic for an obscure product, and unfortunately, you know, obscure products are like 80% of what companies are selling on average, you know, it's obviously at the tail. Then you will realize that you have only a handful web visitors per day. So it's not, yes, you might have millions of clicks, but when you scale it down to the time scale that matter, which is usually the day or within the day, because your supply chain decisions are taken on a daily basis or even sub-daily basis. If you look at the granularity that matter, which is the product, the reference, at the lowest level, so the exact size, the exact color, shape, you know, the exact variant, not a generic product, because on supply chain you don't decide to produce, you know, a generic T-shirt. You produce a T-shirt of this color, this size, this shape. So when you start to look at the lowest level, which is the one that matter, you go back to data that are limited. So yes, people are saying they are doing big data, but the reality is when you look supply chain through the eyes of what is relevant, it's not that big actually. And the biggest, and I wish it was, but because from a statistical perspective, it would be so much easier, you know. But this is not the case. So don't be confused. I believe this big data gives people, you know, it's super misleading because you can think, oh, that's okay, I have millions of data points. No. Again, if you're looking at a factory, even a factories that produce millions of units, the question is how many batches are you producing? And maybe in terms of batches, you have something like a single digit number of batches, and you've only had the factory operating with this mode for the last 2 years. So we are talking of a few hundred batches, and this is it. This is not big data, even if you collect large amount of data.
Okay, we'll have to leave it there with the bombshell that in terms of data, less is maybe more. So that's everything for this week. Thanks very much for tuning in, and we'll see you again in the next episode. Thanks for watching.